Calculus functions as a precise dimensional translation layer, a mechanical engine for building geometry out of coordinate data. The equation y equals the square root of 9 minus x squared defines a relationship. Calculus projects it into 3D. First, optimization isolates single critical limits. Next, integration calculates the 2D area beneath the curve. Finally, rotating that plane constructs a solid 3D volume. We will build this pipeline step by step, demonstrating how these equations provide the geometric blueprint for a three-dimensional object. The first stage of our pipeline is optimization. This is the mathematical process used to identify the peak efficiency, or the structural boundaries of a system. Consider the rational function f of x equals x plus 1 over x. It creates two mirrored branches separated at 0. To find structural limits, we look for critical points where the rate of change hits 0, represented by a perfectly horizontal tangent line. We calculate the first derivative and solve for 0. The resulting math identifies two specific coordinates, x equals -1 and +1. Let's analyze the curve at x equals -1. Approaching from the left, the slope is positive, then turns negative. This up-to-down transition forms a peak, identifying a local maximum of -2. Now observe the behavior at x equals +1. The slope moves from negative to positive, forming a trough. This confirms x equals 1 is a local minimum with a value of +2. This creates a unique optimization paradox. The peak we found at -2 is numerically lower than the trough we found at +2. This occurs because the discontinuity at 0 prevents the two branches from interacting. It clearly shows that 1D optimization identifies local structural limits, regardless of exactly where they sit on the vertical scale. With our critical points identified, we can move up a dimension to measure the flat area trapped underneath a curve. We will use the function y equals x squared minus 4, focusing on the space between the curve and the horizontal axis, bounded by the lines x equals 3 and x equals 5. To calculate this total area, we use the definite integral. We first confirm the curve does not cross the axis inside our interval. The 0 crossing at x equals 2 lies safely outside our integration zone. Since the function remains positive, we integrate directly. The integral calculates this space by summing an infinite number of microscopic vertical rectangles filling the gap. This is represented by the integral from 3 to 5 of x squared minus 4 dx. Solving this requires finding the antiderivative. By the power rule, x squared becomes x cubed divided by 3, and the constant 4 becomes 4x. We evaluate this at our upper limit of 5, which gives us 125 thirds minus 20. We then evaluate it at our lower limit of 3, yielding 27 thirds minus 12. Subtracting the lower value from the upper value gives us a precise area of 74 divided by 3 square units. The definite integral has successfully translated a continuous, one-dimensional line into a perfectly measurable two-dimensional plane for us to analyze. In the final stage of our pipeline, we rotate this planar space to generate a solid three-dimensional volume. We return to our initial function, y equals the square root of 9 minus x squared. This equation defines an upper semicircle sitting on the origin. To generate a solid sphere, we take a single slice of area. Rotating it around the axis traces a cylindrical disk. With a radius of the function's height and a thickness of dx, summing infinite disks gives the volume, pi times the integral squared. We apply this formula to our semicircle equation. Squaring the square root perfectly cancels the radical, leaving us with the simple expression, 9 minus x squared. Because the shape is symmetrical, we can simplify our calculation by integrating from 0 to 3 and doubling the result. The antiderivative evaluates to 18. Doubling this and multiplying by pi results in a volume of 36 pi. As the area sweeps around the axis, the algebra constructs a solid sphere with a volume of exactly 36 pi. We have successfully used a one-dimensional equation to define the three-dimensional volume of a physical object. This dimensional journey shows how calculus constructs geometry, moving from isolated points to solid volumes. We use derivatives to map structural limits, identifying peak efficiency and critical boundaries. We used integrals to capture and measure flat planes trapped beneath a curve. And we used the disk method to push those planes into the third dimension to create solid volumes. Each of these spatial results is produced by its own underlying math engine. The utility of these operations goes beyond solving for an unknown variable on a page. Advanced calculus provides the systematic framework for translating abstract algebraic limits into the measurable dimensions of our three-dimensional world.